Polar graphs part 2, what we're going to do here is look at 3 more of the classic type curves that we can get. The first that we're going to look at is a rose. A rose is of the form r equals a cosine n theta or r equals a sine n theta. Okay, so again, you can either have a cosine or you can have a sine. We are allowed to have factors that are out in the front. You can probably anticipate what that would actually do to the graph as you've seen factors in front of functions before. All right, but we also have an n value that would be multiplied by the theta, and all of that happens inside of your trig function. Okay, so then we need to look at what that does. All right, at the bottom of these pictures, we do have a little bit of information about how that n value works. If the n value is even, then you're going to get an even number of petals. Okay, but what you're really going to get, and you're going to see this in a little bit, is that whatever the n value is, you're going to get twice as many petals as that number would be. So this one has a total of 8 petals in here, which would mean that the n value is actually a 4. Okay, whatever you have for the n value, you're going to have double that number of petals. All right, and if n is odd, you are going to get an odd number of petals. In this case, whatever the n value is, that will be the number of petals that you get. So this would have an n value of a 3. All right, so again, this n value would be 4, but you get 8 petals. This n value would be 3, and you end up getting 3 petals. The orientation of the graphs is all going to depend on whether or not we have a sine or a cosine type function here. All right, for example 1, what we're going to do is take a look at a graph of a rose. All right, so the equation that we have is going to be r equals 2 cosine 3 theta. So as I had mentioned beforehand, because we do have a 3 here, you have an odd number and it's a 3, that means that you are going to end up with 3 petals in the graph. All right, so I've already got a lot of values put together here that we can reference and then just plot it. That way we don't need to build a table in the calculator. All right, at theta is equal to 0, you get a radius of 2. Okay, so at 0, you're going to get a value out to that point. So you might already be figuring out what the 2 does to the overall rows that we have as a graph. Next, pi over 12. We haven't done one of those before, but that's going to be this line right here. This is going to be pi over 12. So I've actually got this quadrant that's broken up into 6, so that would be, this is all pi, so each of these is a 1/12 of a pi here. All right, so we are going to be plotting at 1.4. Okay, that'll give you 1, and then these are, you got 5 rings in between each of these, so you can count these as 0.2, 0.4, 0.6, 0.8, so on. Okay, so that one's actually pretty easy to plot. That will be right here, that'd be 1.2, and then this is 1.4. All right, so pi over 6, that will be here, that's pi over 6, and for that, we get a 0. Doesn't actually go anywhere from there. All right, so our dots right now, we've got one here, we got one here, we got one here. Hopefully you can start to see that that is going to create a petal. If not, we're gonna see it in just a little bit. All right, so pi over 4, which would be located here, that is gonna be at -1, okay? So it actually goes through and it ends up at that location. All right, so it appears as though it's doing this sort of business, at least that's what we can tell from these dots. All right, pi over 3 is gonna be right here. We get -2. All right, so that's gonna be down here. That's where we're gonna end up. 5 pi over 12. All right, so each of these is a 1/12. That'll get us right to there. Okay, so this is 5 pi over 12. That'll be at -1.4. Okay, so I'm looking at this as being one line away from that axis, which is going to make it 1 this direction. And we're going to end up right there. That'll be our point. Pi over 2 is going to give us 0, so we're back at this spot. Okay, we're back at that spot. So if we're trying to watch some of these, it seems like we're doing this, coming through, we hit that point, we're going to come back around into the origin, and come through the origin, so let's see where we go from there. 7 pi over 12 is going to be right here. Let's get that, 7 pi over 12. And that would be at 1.4. Okay, so in that direction, we're here. 2 pi over 3 is right here. 2 pi over 3, 2/3 pi. That will be at a 2. We're at a 2 there. 3 pi over 4, right there at 1.4 at that point. 5 pi over 6 is going to be back at a 0, which we've already marked several times, but this might be hard. We want to remember that we're coming back to that spot. So far it's looking like this. This is what our picture is doing. It's going back to 0 there. All right, and then 11 pi over 12, that would, each of these is a 12, so that's going to be over here. 11 pi over 12 at that spot. Did I skip one here? 5 pi over 6, I did skip that one. Oh, no, that was the 0. That was the 0 one. All right, so 11 pi over 12 is going to take you back through at 1.4, which sort of looks like the one that we've got right here. And then last, at pi, you're going to be at -2, which will just put you back to the place that we started at. All right, so if we follow all the dots, it looks like it does this. We started here, it comes around and through, back through the origin, and here, and then back around, and those will be your 3 petals. All right, let's go ahead and verify it in the calculator just to see that this is true. All right, so we got 2 cosine 3 theta. Okay, and I believe my windows are all set correctly. And of course, this is in radians here. Okay, we're using radians for all this. Go ahead and graph. All right, and that's the picture that we get. Let's do it. I don't know if I can make it go slower, but I want to see that it actually does start here and then it finishes back at that spot. Okay, so let's see if we can get it to show one more time. Okay, super fast. I think that it actually did that. All right, so here's our graph. Where's that dot? All right, and that'll be your 3 petal sort of look. Some things that we could consider, like just for the sake of learning a little bit more here, what if we just change that to sine? Let me backtrack for a moment here. The 2 tells us the length of the petals, right? That would be the furthest distance that we have away from it. The 3 is going to tell us how many petals we have. The cosine is going to give us the orientation that we have. So if I change that to just a sine, and graph it, you're going to see that we still get generally the same shape, except that it's been rotated a little bit around. You've got, instead of a petal following that positive x-axis area, it seems to be following the negative y-axis area. All right, the next type of graph we're going to look at is called a Lemnisqueet. Okay, and ultimately when it's graphed, it basically is just an infinity symbol. That's what it turns out to be, except that the orientation can be a little bit different depending on whether we use a cosine or a sine. All right, the form of the equation is going to start like this, r squared. So that's a little bit different than the others we've looked at. Okay, we've got r squared is equal to a squared cosine 2 theta. We could have that, or it could be r squared equals a squared sine 2 theta. And again, the cosine versus the sine is going to be the orientation that we do have. All right, in front of the theta, that is going to be a constant 2. Okay, so that part's not going to change. This is not an n value that you could switch out. It will just be a 2. Okay, but we can change the a values, and depending on how you change the a values, that will change the size of the Lemnisqueet. For example, 2, we are going to graph r squared is equal to 16 sine 2 theta. All right, now remember that from above, the outline of this is going to be r squared equals a squared. Then it's either sine or cosine 2 theta. All right, so the 16, if that would be your a squared, that means that the a value is 4. That's the value that we're really thinking of as a, but it becomes squared and looks like the 16. All right, so I have a table of values here that we can use to go ahead and start graphing this thing. Add 0, you get 0. Okay, so that's right there. Add pi over 12, which is going to be right here, pi over 12. I got 1, 2, 3, 4, 5, 6 increments. Okay, and then full pi, so that would actually just be a 1/12 of a pi. And this is where it gets kind of weird because it says r squared. Okay, because it says r squared, you can actually have a response of either the r value either being a positive or negative 2.8, because when that number becomes squared, it still matches the other side. Okay. All right, so we actually get to plot 2 different points for pi over 12. We're going to have that positive 2.8, and then we're also going to have the negative 2.8. The rings that I'm using here are different than the last one. What I'm gonna do is count by twos. So I have 2, then I've got 4, which means that right here, that would actually be at a 3. So these are actually half increments that we have. All right, so 2.8 off of this, that would be 2. That would be 2.5. This would be 3. So we just sort of have to estimate that the dot is gonna be about here. All right, and then in the other direction, same thing. It's gonna be about that location. Let me go ahead and erase that little mark for the 3. All right, next, pi over 6. Pi over 6 is gonna be here. We're gonna have 3.7. You have 3.7, so that's 4. That would have been 3.5 right there. So again, it's just kind of like partially in that spot. And then I'm gonna go backwards, match that up with this point. Okay, then pi over 4, right here, we're gonna get right at 4, so that one's easy to mark off, and then you'll get, you also get 4 right there. Pi over 3 is gonna be similar to that 3.7. Okay, so that's about here, and it's about here. I'm really just using the other ones to kind of balance, make those look the same. 5 pi over 12 will be here. 5 pi over 12 will be here. 2.8, we did that one before, so I can kind of mimic what I had done for the other dots here, and let's see if I get that one right. Then it should be right about there. All right, and then pi over 2. Look at that, it only takes a fourth, like of the whole rotation here, to get all the way back to 0. Okay, so if you remember the order of the coordinates that we did, it plotted starting here, it goes to that spot, and then around, and then from here, because it had to match that point, I almost forgot which direction it went, it's gonna go through and then back around to there. That's gonna be the shape of our graph. All right, so let's check it out. Well, I'll type it in just a moment so we can see it, but this was the order that we had plotted the points. Sort of, because it also had built the other side while we did that. So I guess that wasn't 100% true. But when we do connect them, we're gonna get that shape. There we go. All right, so let's take a look at this in the calculator. All right, so the funny thing about it though is this starts with r squared, which is not something that you can type into all calculators. So the type of calculator that I have, what I need to do is take a square root. I have to take a square root of that side so that I can type it in. But when I do that, I need to be conscious of this positive or negative sort of thing here. When I square root the other side, I can't just treat it as a positive, otherwise I'm only gonna get part of the graph. So I actually gotta type it in twice, but with a negative for one of them. Okay, I need to trick it so that it'll graph it again here. All right, let's see this happen. It'll be in 2 different colors, but it should create the whole image. There it is. All right, so when the blue one is done, like when the blue one graphs, it doesn't actually complete the rest of it, and then the red overlaps a lot of it and creates the rest of the graph. But that is it. That is your Lemnisqueet. All right, I got one more type of graph that I'd like to look at here, which is a spiral. The equation for a spiral is pretty simple. It is simply r equals a times theta. So this equation does not involve sine or cosine in there. It does not have the trig functions in there. It's just simply a value multiplied by theta. Now that value could just be 1, so you could even get something as simple as just r equals theta, and that would graph a spiral, because as theta increases, so would the r value if they were equal to each other, right? Now, if you do have a value greater than 1, you are just going to see the spiral grow faster. All right, so we're going to go ahead and make a graph for r equals 3 theta. And again, like the other ones, I went ahead and provided a table of values. All right, so when theta is equal to 0, if we plugged in a 0 for the theta and multiplied it by 3, we would still get back a 0. Okay, so our first point is going to be right here at the origin. All right, next, pi over 4, which is going to be right here. That would be pi over 4. That will be at 2.4. That would be at 2.4. All right, so my rings right here, I'm counting by tens, and then I've got 1, 2, 3, 4, 5. All right, so every one of the lines is going to be a 2. Okay, so 2.4. be pretty darn close here. That would be at 2, that would be 4, so just slightly past that point. All right, so that's where we're going to be at there. Pi over 2 is going to be at 4.7. Okay, so going up, that'll be 1 ring. 2 rings will get me at 4, and then right in the middle would be at a 5, right? So we got 2, 4, 6, 8, 10. All right, so we got 2, 4, that'd be 5. So it's pretty close to that number. We'll just put the dot there. It's about as close as we can get. All right, at pi, we can go all the way to pi now. We're at 9.4. That is going to be about here. 3 pi over 2. All right, so we're going to jump all the way down to this part here, 3 pi over 2. That will be at 14.1. Okay, so that'd be 12 and that'd be 14. So you can pretty much just put it right there. All right, so if we're watching the dots here, you're going to see them moving in a circular motion, of course, because we are following the rotation that we have here, but they are getting further away from the center, so it's starting to make that spiral. 2 pi is 18.8. That would be 18. It's a little bit closer to 19, so it's about there. And then 3 pi. All right, so that was 2 pi. So 3 pi is all the way back over here, right? This would be pi. That would be 2 pi. This is going to be at 3 pi. That'll put us at 28.3. So that's about here. All right, so we're seeing our little dots just sort of move around and go to that spot over there. All right, let's go ahead and take a look at this in the calculator, and then I'll attempt to make a sketch of this. This one's going to be a little bit of a hard one. All right, so what I'm going to go ahead and do here is show you what this looks like when you're setting up a window for this type of a graph. All right, so for our thetas, the smallest theta that I used was 0. So I'm going to keep that. The largest that I did was 3 pi. Okay, so I'm going to go to theta max, type in 3 pi, which will give me that number. Okay, and then the steps, we don't really worry about that. All right, for the x's and the y's, the minimums and the maximums, that would have to do with the window that you're actually looking at. What I did here was about -30. Okay, -30, and then we'll just go to +30 for the other end. And for the y's, for the y values here, I've got -20. You can't see that on screen, but I go down to about -20. Actually, let's just do -30. And the max will do 30, and then I'll square up the screen. All right, so then the equation is simply 3 theta. We hit graph. There's our spiral. It's a bit squished because how the screen is set, so I'm going to go to zoom. Going to hit 5 to square it up. Okay, and that'll give you that true looking spiral that we have. And then now what I do is I attempt to draw this thing, which I probably won't do too great of a job. I did have it stop at that spot, but notice if I go, let's see if we did like, we'll do 4 pi. You'll see that it continues on to 4 pi, and then I could even go further and keep showing that it continues to spiral out. All right, but for what we've got, this ain't gonna look good. Okay, that's about the best I'm gonna do. These are hard. I feel like if I highlight it a little bit here, maybe it'll hide some of the defects that we've got. Okay, we'll let that be.
Later, blah.